Valentine's Day, everyone, and welcome to our MPRINT Hub webinar. Today we'll be talking about human milk at the intersection of maternal and pediatric therapeutics. So fitting in onto that lactation component of our maternal health standpoint. We have Dr. Lars Bode and Dr. Christina Chambers here today to present some of their work with the MPRINT Hub and related to their Centers of Excellence in Therapeutics from University of California at San Diego. Dr. Bode is a professor of pediatrics and chair of the Collaborative Human Milk Research Network and director of Mother Milk Infant Center for Research Excellence, or the MOMI Core. And Dr. Chambers is a professor of pediatrics and co-director of the Center for Better Beginnings and the co-PI on the UCSD MPRINT Centers for Excellence in Therapeutics proposal. So with that, I will pass the microphone to them.
All right, thanks very much. Share my screen real quick. Hello, everyone. Good morning or good afternoon. All right, I'll get started, and then Tina Chambers will be taking on the second half of the presentation as we talk about human milk at the intersection of maternal and pediatric therapeutics. And just to set the stage, what this MPRINT is and what the different centers are, just a quick introduction here. So we have this NIH funded MPRINT, and MPRINT stands for Maternal and Pediatric Precision in Therapeutics. And that consists currently of the Knowledge and Research Coordination Center, where Sarah is. And then we have two centers of excellence, one at Vanderbilt University and one here at the University of San Diego. And that's not just Tina and Lars, that is multiple other people. The lead PI here is Adriana Tremoulet, who's pictured on the top there. And then there's multiple other people that have a very strong track record on maternal and pediatric therapeutics, but we also have a very strong interest in human milk. And just to put this a little bit on the map, how that looks like at UC San Diego, we have multiple different entities that work on human milk, including a state-of-the-art human milk bank that really feeds into, no pun intended here, that feeds the preterm infants with human donor milk. And then we have a research center that I'm running called MOMI Core. We have MPRINT that fits into that. And we also have the Mommy's Milk Human Milk Biorepository that Tina is going to talk about later in this presentation. And then we have analytics cores, we have education components, and it really sits at this very intersection of health sciences, research and discovery, education, clinical care, and public health and global health, really. So that's why human milk is of such interest to us. And to lead into the topic today, I took this figure here from the 2021 paper that was actually published by the NICHD program officers, Shaja Ren and Andrew Bremer and Aaron Pavlik. And I find this figure here quite telling because it really tells the statistics and the problem that we're dealing with. So it says that 60% of pregnant women that take one or more prescription medications for pre-existing or pregnancy-induced conditions, 60%. 70% of women who breastfeed or pump their milk take some form of medication during lactation. And now the big problem is that 90% of those clinically approved medications do not have any appropriate drug labeling for pregnant or lactating women. So although it is a very common practice to take medications, we have very little information on most therapeutics in the space of pregnancy and lactation. So that's really the big elephant in the room. Now, is it really such a big elephant? Yes, pregnancy, we can't really do much about it. We have to still get pregnant to save the human race, but do we really need to breastfeed? There's alternatives. Do we really have to worry about this if a woman takes medication? Can we just stop breastfeeding and take infant formula instead? Why are we so interested in human milk? And I'll give you a few statistics on why we think that's so important. So here is a sentence from the editorial in the Lancet Breastfeeding series that says that the death of 823,000 children and 20,000 mothers each year could be averted through universal breastfeeding. And that comes along with economic savings of $300 billion. And we're trying to find out, what's in human milk? How does this all work? What's the molecular mechanism that drives this powerful message that human milk saves lives? And just to give you a few examples, if we look at diarrheal disease, we lose still about 2,200 infants every single day from diarrhea. On the other hand, we see that children who are breastfed have a substantially lower risk of developing and suffering from infectious diarrhea as well as respiratory infections. So the question is, what's the link here? What's in human milk that protects from diarrheal disease? In the preterm infant space, we see a disease called necrotizing enterocolitis. About 5% of all very low birth weight infants develop this often deadly disorder. And on the other hand, we see that human milk can save lives. Once again, preterm infants who receive human milk are at a 6 to 10-fold lower risk to develop necrotizing enterocolitis. So what's the connector here? We also see that the benefits extend to later periods of life, really throughout the entire lifespan. We know that infants who received human milk early in life are at a lower risk to develop overweight and obesity, have a lower risk for diabetes later in life, and potentially are even smarter. And again, the question is, what is human milk doing in these areas that drive all these benefits? And it's not only good for infants, it's good for mothers as well. So we see that women who breastfeed have a lower risk of diabetes later on, have a lower risk for cardiovascular disease, and have a lower risk for breast cancer and ovarian cancer. So lots of benefits really that we don't want to miss out on by women being on medications and then telling them, oh, just stop breastfeeding, you just feed formula instead. All right, so bringing it back to this, we think that lactation here is central, that we need to find a solution for these 70% of women that are on medication. We don't want to tell them to just stop breastfeeding. Now, that's why is this so important, and what do therapeutics have to do with human milk? Of course, the traditional question that comes up here is, if mom is on medication, is that medication somehow making it through human milk to the infant? Are there safety concerns? And this is human milk serving as a vehicle for that therapeutic. But there's potentially other aspects. This part, Christina Chambers is going to talk about and explain how we're addressing that with the biorepository, and gives a few examples on coronavirus and the vaccine that we're working on right now. So I leave that to the second part, but I want to talk about a few other things that we're not thinking of, particularly when we think of therapeutics and maternal infant health. So what about maternal therapeutics changing human milk composition? And what effects does that have on infant health and development? What if human milk components affect pediatric therapeutics? So this is now infants, children getting therapeutics, but also receiving human milk. Does that have an effect on absorption, on distribution, on metabolism, on excretion, efficacy, safety, toxicity of those drugs? And last but not least, can we learn from Mother Nature and actually take a look at the many human milk components and use them as templates for therapeutics that we can use to combat some of the diseases we're struggling with? Okay, so let's start with maternal therapeutics altering human milk composition. I'll give you a couple of examples there. So what is in human milk? What do we start with? Of course, human milk is mostly water, but there are many other components as well. There's carbohydrates, mainly lactose, but also oligosaccharides. And I highlight this here in red because some of the examples that I'm going to bring are on oligosaccharides. That's my pet peeve. My focus of research is on human milk oligosaccharides. Then we have lipids in human milk, very complex formation sitting in this tri-layer captured particle called the milk fat globule. Lots of bioactive components in there. We have proteins that can be just proteins, peptides, but those proteins themselves have some activity, have enzyme activities that contribute to the digestion of other milk components, but could potentially also digest some of the protein-based therapeutics. And then in addition to that, we have cells in human milk, we have bacteria, viruses, fungi, we have vitamins and minerals, hormones, and many, many other things. So milk is really this complex fluid, this complex tissue almost, because we have cells in there as well. And all these components interact with each other. And really, it's not just a list of bioactive ingredients. We've shown this here as a perspective article in Science a couple of years ago, that human milk does not stand in isolation. It really depends on what we call the mother milk infant triad that now is embedded in an environment that has socioeconomic, cultural, behavioral, and other contexts. And depending on those contexts, human milk has to deliver different things. So you can imagine the sterile NICU environment here in San Diego, probably a very different context than a low middle income country in the field somewhere in a different continent. So human milk has to deliver very different things to different infants, and also maternal factors and infant factors that drive this. So it's not as simple as we have one ingredient and it's doing X. It has to be seen in the context. And most importantly, that context and that entire triad changes over time. Human milk composition is not constant, changes over the course of lactation, changes by season, changes during the day. In fact, it changes during one feed. Milk composition at the beginning of the feed is different than at the end of the feed. So in all that, we now have to also think about therapeutics. And the first example I want to give here is on the COVID vaccine. So now we're entering a COVID vaccine into this triad, and what does it do? And this is really work, and Tina's going to talk about this more in detail later, that comes out of the human milk biorepository that we have at UC San Diego, that was able to collect multiple samples already during the pandemic from women that were infected, but then also women that got the vaccine. And then my lab in the center went in and studied those milk compositions for different antibodies against the vaccine. And just to make this really quick, just as an example, we see indeed that IgA, IgG come up in milk, and time dependent here, depending on where the dose is, what brand of vaccine was given. You see down here, J&J, for example, hardly any response in antibodies. So there is a milk component or multiple different milk components that change or are introduced when we introduce a therapeutic. So it's, of course, the vaccine-specific antibodies that we can measure, but does it change other milk components as well? And that's something we're trying to find out right now. Does it change proteins? Does it change lipids? Does it change oligosaccharides? So we don't know anything about that, on how different therapeutics change milk composition. And as a second example here, where we did a study a few years ago, this is an intervention study in Finland, where the group delivered a probiotic intervention to Finnish moms during pregnancy, and then until birth, and we were able to measure milk composition afterwards during lactation, specifically focusing on the oligosaccharides, and we found that there are indeed differences. So the group that received the probiotic during pregnancy had different oligosaccharide composition later on during lactation. And without going too much into detail, so we see that a probiotic during pregnancy changes milk composition, specifically for oligosaccharides. We haven't looked at other milk components at this point, but what about other therapeutics like antibiotics? If probiotics can change milk composition, what about antibiotics that are commonly used? And what about all the other therapeutics that are given? Do they change milk composition, and what are the consequences? So these are just two examples, but really shows you how little we know about how maternal therapeutics alter human milk composition. Now, the other point here is how human milk components affect pediatric therapeutics. And I think one of the things to keep an eye on is the microbiome. There's clearly interactions between the microbiome and drugs, and that's shown here in this review paper here by Zimmerman, where they highlight how different microbial communities change the efficacy, toxicity of certain drugs, and the other way around, how certain drugs now change the microbiome. So it's a very intricate interplay between the two. Now, what drives the microbiome in early life, in the first year of life? If you look at this study here by our colleague Chris Stewart, it was published in Nature a few years ago, they looked at the variants and factors that drive the microbiome over different periods of time in life. And in the first year of life here, clearly you see there is this pink bar that sticks out as being mostly significant, mostly important for driving microbial composition, and that turns out to be breast milk. So breast milk is the strongest driver of microbial communities in the first year of life. So if we go back to this figure here by Zimmerman, we probably have to add this milk and this era where we know that human milk and human milk components strongly affect the microbiome, and with it, this interplay between microbes and therapeutics. Here's a second example, how milk components interact with therapeutics. This is a study that we did with Victor Nizet and a postdoc back then in his lab, here what we did is we took several pathogenic strains, group B streptococcus among them, and added human milk oligosaccharides to them to see how well they grow or if they stop growing. And indeed, you see that group B streptococcus in the presence of human milk oligosaccharides simply stops to grow. And other groups have shown this and confirmed this in the meantime. We were able to identify one specific structure in these oligosaccharides. We identified the target on GBS, at least narrowed in on that. We have some kind of what the mechanism might look like. What we don't know is how common is this? is there other pathogens out there, other bacteria, other viruses, where milk components go in and stop their growth or kill them altogether? But the reason why I'm really showing this here is, what we also showed is that the human milk oligosaccharides synergize with antibiotics. So there is this milk component therapeutic interaction. And if you look at the values here, IC50 for the antibiotics drops significantly in the presence of human milk oligosaccharides. So a clear interaction between a human milk component and a therapeutic in the pediatric space. Okay, not too many other examples on that. I want to focus here on that last part, how human milk components can actually serve as templates for therapeutics. How can we learn from human milk to develop new therapeutics? And wonder, wait, didn't we just see this slide here before? So you're running out of slides now. I just want to bring this back because it really highlights that there are human milk components that act as antimicrobials. In fact, many of the human milk components were developed through evolution to help protect the infant from pathogens and many other things. So how can we take this information and develop potentially new antimicrobials? And is there a need for that? And clearly there is a need for that. I took this graphic here from UC San Diego's CHARM website that Victor Nizet is also running. CHARM stands for Collaborative to Halt Antibiotic-Resistant Microbes. And you can see there's like this yellow part here in the pie chart that stands for AMR, and AMR stands for antimicrobial resistance. So a huge threat to humanity, really, if you want, where the WHO has projected that we're losing about 10 million lives every single year by the year 2050, just based on those antimicrobial resistant strains. So a huge problem. But human milk components could potentially be part of the solution. So if we mine human milk components for some of those antimicrobial resistant bugs and how they could potentially stop them from growing, I think that is a huge opportunity for us to intervene in this looming crisis here. Okay, second example is back to necrotizing enterocolitis. So again, we know that still about 5% of all very low birth weight infants develop necrotizing enterocolitis. And we see, on the other hand, that preterm infants who receive human milk have a much lower risk to develop this disease. So if we were able to identify what the components are in human milk, we could potentially develop a new therapeutic. And that's really one of the flagship projects that we had in my lab for a long period of time. So this slide here is really 13, 14 years of work in one slide combined summary. So we set out and said, well, maybe it's the oligosaccharides in human milk because they're not an infant formula. They're unique to human milk. So maybe that difference drives this benefit from human milk against necrotizing enterocolitis. So the way we tested this was we isolated oligosaccharides from human milk, pooled human milk, and then tested this first in an animal model. And it worked tremendously. It improved survival quite a bit and reduced pathology scores very nicely. And we then set out to identify, well, which oligosaccharide is, there's about 150 different ones. Can we identify that one structure that is responsible for this positive effect? And indeed, after several years, we found that this particular oligosaccharide structure, short DSLNT, is responsible for the positive effect in the animal model. Now, we always got the criticism, well, it's an animal model, you make a rat sick and then you cure it afterwards, congratulations, but how does this really translate to humans? And to address that point, we designed a couple of mother-infant pair cohorts where we recruited moms and the very low birth weight infants, collected milk samples about every second day throughout the first 4 weeks of life. That's where NEC happens most of the time. And then analyzed those milk samples for oligosaccharide composition and saw, okay, is the oligosaccharide composition somehow associated with necrotizing enterocolitis risk? And when we did that, we found that is exactly the case. And it's the same oligosaccharide that we found to be protective in the animal model is also associated with a lower risk of NEC in the human cohort study. And we've since done this in a cohort here in North America. We've repeated that in a cohort in South Africa, and just recently published a paper and got as well with Chris Stewart's group, where we found the same oligosaccharide being associated with necrotizing enterocolitis in the UK. So 3 different continents, 3 different cohort studies, the same oligosaccharide popping up as being associated, and the same oligosaccharide also working in that animal model. So that gives us a greater confidence to move forward into a clinical trial if the oligosaccharide becomes available. And we're also studying the mechanism in the back end. So the link here could be oligosaccharides. In fact, it could be one specific oligosaccharide, as we have shown that this specific oligosaccharide is associated with lower neck risk in the cohorts. We've also shown that the same oligosaccharide improves survival and neck pathology in the animal model. So that gives us a great opportunity to develop therapeutics based on this component in human milk. But it also gives us an opportunity to screen mom's own milk and donor milk products to see if they have sufficient or insufficient amounts of these milk components that then protect the infant from this disease. Now, unfortunately, the oligosaccharide composition analysis is fairly tedious, and there's really only a few labs in the world that can do that. But what we really want is a point of care measurement of these oligosaccharides. So wouldn't it be great to have like this little device where you drip in a little bit of milk and then it sends to your cell phone, you have low or high levels of these specific oligosaccharides. It's a dream, of course. So it would be great if we could do that. In fact, we might be able to do that. We've recently published a paper last year where we've shown exactly that for one of the oligosaccharides, 2FL, not DSLNT, but 2FL, where not only can we say 2FL is there or not, but we can actually quantify it. So we can drop in this drop of milk on a chip, and then shortly after, over Bluetooth, it gets sent to your iPhone, and it tells you you have this and this much 2FL in your milk. And now the idea is, of course, to expand that and build a sensor that can detect DSLNT as well. So you can take that into your NICU, see, milk sample has sufficient amount of DSLNT, you're good. Or let's say you have a milk batch from the donor milk bank that has low levels of DSLNT. You would say, well, let's grab another batch, or let's add some DSLNT to it to be on the safe side. So that's really what we're trying to do here, and that could be the future for necrotizing enterocolitis. One more example before I hand it over to Tina, and that is human milk oligosaccharides and in the context of chronic macrophage inflammation and resolution. And this is a project really led a good friend of mine, Philip Gortz, at UC San Diego, where we said, well, what happens if you throw my oligosaccharides onto your macrophages that you're working with? What happens? So it's really just it was started out as a fun project, and we did that, and we found, if we stimulate macrophages with LPS and then add human milk oligosaccharides to it, the inflammation response is extremely blunted. And we then again set out to identify which oligosaccharide is it, and we found that 3-sial lactose in this case was most efficient. And we tested this in mouse cell lines, we tested this in mouse primary cells, we saw that this also works in human cells, this works in human patient cells as well, where this is very important. And it's not just the mRNA is changed, but really this works on a protein level. So we all of a sudden had a component from human milk that, at least in tissue culture, dims down the response of macrophages. And we found later, we looked at the mechanism, that it's actually not less switching on the macrophage, but it's faster switching off the macrophage. So you get the macrophage excited, so to speak, and then it does its thing. And if it does that too long, it creates a lot of damage. And we were able with 3SL to reduce that and shorten the time of the active macrophage. Now, where is that important? Where do we need activated macrophages, and what can we do to stop something like that? Rheumatoid arthritis is one example. We know that 1% of the world population suffers from RA, 1.3 million people alone in the US, and it's mostly women. So 3 times more women develop arthritis than it is men, but women may actually hold the key here to stop that inflammation from happening. So we took the tissue culture work and took it into animal models and worked together with Maripat Kaur and Nunzio Bottini at UCSD to test out what happens if we give 3SL to an RA model. So the way that this model here works is we give collagen antibodies to this animal to start with, and it starts out with a non-diseased paw, as you can see here. And then the paw swells up We give it LPS challenge, and then the paw really swells up. But if we take another group of animals and give them 3SL instead, you see that that swelling is much, much lower. So we see in an animal model that this indeed works. Oral gavage of 3SL twice a day did that nicely. And not only was it the swelling, we looked at inflammation markers, bone erosion, cartilage damage, and you see that 3SL had a significant impact on all these markers. In a second model that was more spontaneous, it worked as well. So 3SL nicely reduced the ankle thickness and the clinical scores in this RA model. So what is that to do now with pregnancy and lactation? Took us a little bit to get that curve, but what we heard was that some women with RA go in remission during pregnancy, and then RA flares up again later in lactation. So it turns out that we actually find these oligosaccharides, and mainly 3SL, already in the maternal circulation at the end of the first trimester. So those two time points when RA goes in remission and when these oligosaccharides appear in maternal circulation coincide very nicely. So is there a potential link? Very difficult to test this, of course, but we were able to team up with our colleagues in Canada that run the child cohort study. And there they had reported whether moms never had RA, so that's our 0 group, whether they had RA, but then currently not having RA while they're breastfeeding, so that's our remission group. And then we have moms that reported RA before and they still have it, so these moms did not go in remission. And we had access to the oligosaccharide measurements that we did in milk before, and we found that no difference in total oligosaccharides, but a significant increase in 3SL in the group that actually went in remission. So it feeds a little bit into our narrative that high concentrations of 3SL would potentially slow down macrophage inflammation and then leads these women to go into remission. Lots of limitations for this study. It's really just a proxy, but it gives us a good hint that this might be actually working. Okay, so that's arthritis, where 3-sialactose, a component from human milk that we can make synthetically, could be a potent therapeutic to treat this disease. One more example, also on chronic macrophage inflammation, now going in a different direction. Where else do we need chronic, or where else do we see macrophage inflammation? That's in cardiovascular disease. And here we're losing about 18 million people a year annually. And where does the macrophage play a role here? So that's your foam cells, right? So that's the macrophages that load up with lipids and then eventually clog your arteries and cause either heart attack or stroke, to say it simply. So we took the 3SL component here, and this is also NICHD funded, into a model of cardiovascular disease, together again with Philip, fed them a high-fat diet, and then later treated them with 3SL, or not, as a control group, and measured atherosclerosis afterwards. There's no difference in food intake, no difference in body weight, so that all those parameters all held up. But we see clearly a difference when it comes to lesion formation in the aorta. And we also see differences when it comes to aortic plaque size and necrotic core that we analyze separately. So it seems to work in the animal model here for atherosclerosis as well. All right, so that could be yet another opportunity for a human milk component, the same as we used for RA, to be used as a therapeutic to treat heart attack and stroke, so cardiovascular disease. Okay, so just bringing it back to where we started and going backwards, there is multiple opportunities to learn from Mother Nature and take human milk components as templates for therapeutics. And there I showed you the antimicrobials, then the oligosaccharide for necrotizing enterocolitis, and then an oligosaccharide in a completely different space, now in adults, where we talk about atherosclerosis and arthritis. Then it's possible that certain human milk components affect pediatric therapeutics, maybe through microbiome changes, maybe independent of that. And there I showed you examples, again, on antimicrobial components and how they synergize with certain antibiotics. Then we have maternal therapeutics altering human milk composition. Very little known about that. The COVID vaccine certainly is one example. And then I gave you the example of the probiotic that was given during pregnancy and changes milk composition during lactation. Oops. And then, of course, there is more studied how human milk serves as a vehicle in the transmission of therapeutics from mom to infant and what kind of safety implications that has. And that I hand over to Tina Chambers, and she's going to take it from here. Thank you very much.
Thanks, Lars. All right. Let's see if I can bring this up. Are we good? Are everybody able to see this? I'll bring it to full screen. So thanks so much. I'm going to follow here talking a little bit more about the human milk research biorepository as a contributor to the wide variety of topics that Lars talked about. So this is a nationwide, it's actually US and Canada wide human milk research biorepository, HMB for short, that we established at UC San Diego in 2014 at the Center for Better Beginnings in my division in the Department of Pediatrics, with the express purpose, just as Lars mentioned, that we have a huge gap in our clear understanding of the level of various therapeutics that a person might need to take while breastfeeding in terms of how much actually gets into breast milk, but whether or not that matters. And so that was a primary purpose for establishing this biorepository. But of course, as has been discussed, there are a myriad of other purposes to which these samples and data can be put to good use. So the description of the design and mechanics of this biorepository was published a few years ago in Breastfeeding Medicine. I refer you to that for further details. But basically, we recruit through a number of sources to the biorepository at UC San Diego. What we have in our center, a network of counseling services for pregnant and breastfeeding individuals and their healthcare providers across the US. And that is one source of referral into the HMB. We also have a longstanding 20-year open cohort study across the US and Canada, where individuals who are pregnant enroll in the study and are followed throughout the remainder of their pregnancy, and their infants are followed to at least 1 year of age. And because of the need to study new medications in pregnancy, the 10,000 or so individuals who've enrolled in that study over the years, many of them have underlying autoimmune conditions or immune-mediated conditions, but it's also been a focus of vaccine safety and a variety of other different exposures as well. So individuals who are involved in those two projects, once delivered, if they are breastfeeding, can be referred into the HMB. We recruit also direct to consumer through social media, which has been a tremendous source of identifying individuals who are interested in joining. It's a pretty easy sell, so to speak, that lactating individuals are oftentimes very interested in contributing to this kind of research. And then we also go to specialists, to lactation consultants. Donor milk banks have been very supportive. Pediatricians and pharmacist referrals, and we are able to recruit individuals whose primary language is English or Spanish. We obtain informed consent for the collection of the samples and the metadata, and as part of that consent, individuals are asked to consent to all future uses of those samples and data. Also included in that is an optional genetic consent, which the vast majority of individuals who enroll do agree to. And then they also consent to be recontacted about additional studies or add-on data or sample collections. The samples themselves, we ask that individuals give us a 50 milliliter milk sample as a minimum up to a full expression, although we will accept whatever it is that they can provide. And these can be repeated samples, and certainly we have individuals who enroll with us with multiple children. locally at UC San Diego, individuals can come into our center location and provide the sample there or samples there. But the vast majority, because this is US and Canada wide, we send a kit with instructions, they self-collect, and then they return the samples in a prepaid FedEx overnight shipment to us, at which point we receive them, aliquot them, and we have a freezer bank in our Clinical and Translational Research Institute at UC San Diego, where the samples are barcoded and stored. The metadata is pretty extensive. The enrollees answer questions about demographics, including socioeconomic status, race, ethnicity, occupation, and education, maternal health, previous pregnancy history, child health, breastfeeding habits for this individual with this child and previous children. And then we get a day-by-day, 14-day history of exposures, everything that lactating individual has been exposed to by dose, brand, and indication for prescription and over-the-counter medications, dietary supplements, herbal products, vaccines, and recreational drugs, alcohol, tobacco, and caffeine. We have a standard infant adverse reaction checklist that the person who's enrolled is asked to respond to, and this was developed by Dr. Phil Anderson, who authors LactMed, and is asked standard questions about anything that the parent noticed in the child, change in bowel habits or sleep or irritability and so on. And then we have standard validated questionnaires that the enrollee completes online, measuring stress, anxiety, and depression. They're asked to complete a food frequency questionnaire. And then depending on how old the child is, when first enrolled in HMB, there are neurobehavioral questionnaires sent to the parent that cover the age range from 12 to 36 months. And for a subset, we offer face-to-face testing, which can be done at our center, but we do have projects where we actually travel to test the children. And they provide access to medical records by releasing them on an annual basis for both themselves and their children. We have about 50,000 aliquots in the biorepository right now. This is just showing the US, but we do collect from Canada as well. And just to give you an idea, there are literally hundreds of different exposures reported by these individuals who are enrolled, but these are 24 of the most common exposures. And as you can see, they run the gamut of contraceptives to antidepressants, to thyroid medication, to asthma medications, stimulants, antivirals, and antihypertensive medications. I'll give you a couple of examples, having the HMB existing and people enrolling who just report the everyday garden variety of what they've been exposed to. We've been able to do analysis using archive samples for an exposure of interest. So this particular one was focused on looking at cannabis use, published a few years ago, looking at the first 54 samples we had in the HMB, where the lactating individual reported day by day marijuana exposure in the previous 14 days. And with our collaborators in the School of Pharmacy, we measured levels of delta-9 THC and other metabolites and found that 63% of the samples, delta-9 THC was detectable with a wide range of variability and concentration, largely tied to the number of hours or days since the last use and the frequency of use. But we did find, at least based on self-report, that detectable levels of delta-9 THC were present as long as 6 days after last reported use. This study has since been expanded. We have an additional 132 individuals enrolled who provided samples, and using a more sensitive piece of equipment now able to detect in about 80% of samples delta-9 THC in a high proportion with the other metabolites as well. So the follow-on on this is that these children are all being followed for growth and neurodevelopment to see if levels of cannabis detected in milk are associated or not with development of children subsequently. A second example is purposeful data collection for a new exposure. So having the HMB in existence at the beginning of the pandemic was fortuitous because we were able to immediately pivot and accommodate collecting samples, as Lars said, from individuals who were lactating who became infected, so had a documented PCR positive test for COVID-19. We collected from the first 18 women, 64 samples, and were able to publish relatively quickly that there was no evidence of infectious virus in these milk samples, and subsequently with a larger sample that was just published recently confirmed that finding, no evidence of replication competent virus in milk samples from recently infected individuals, so reassuring from the standpoint of milk itself not likely being a source of infection for the breastfed infant. Similarly, when the vaccination received emergency use authorization in December of 2020, we immediately opened up recruitment for vaccinated individuals, and extended the protocol to be able to include serial samples specifically related to vaccination timing. So we have about 1,200 vaccinated women enrolled, sending samples, predominantly mRNA vaccinated individuals, about 1,000 falling into that group, and fewer with Johnson & Johnson single dose vaccine. These individuals all go through the same standard data collection with the interviews, the medical records releases, and so on, and the neurodevelopmental follow-up and follow-up for growth. And then we added right away an additional 7-day questionnaire following each vaccine dose about mother's adverse reactions using the VSafe checklist of reactions, and infant events as well. So mothers send up to 8 milk samples pre first dose of vaccine, between doses, and up to 90 days post last dose. And some of the initial findings from this were published in Breastfeeding Medicine in August of 2021, looking at the profile of symptoms or reactions reported by the vaccinated individuals and by them about their children. And importantly, we found no evidence of serious adverse events reported by the individual who was vaccinated or by them about their children. A couple of interesting findings, about 10% reported that they had by self-report a change in milk supply, most commonly a reduction in milk supply for a short period of time following a vaccination dose, but returned to normal shortly thereafter. And we had a few women, and this has been reported elsewhere, notice a change in color, but otherwise pretty much unremarkable. So moving on to MPRINT, this project that we're all involved in, as Lars so nicely laid the stage for. This has multiple components to it, but one of the projects is a clinical project that's based on using this HMB infrastructure to carry it out. So the premise, as Lars has just explained, is that establishing the infant gut microbiome was dependent on this dynamic maternal-infant microbiota exchange during early life, and this is in part facilitated through breastfeeding. We also know that antibiotic use is ubiquitous in the US and elsewhere, and that there is evidence that antibiotics are more commonly used in females than males, and that antibiotic use is relatively common in the postpartum period for a variety of different indications. And so for these reasons, this project was structured to better understand the impact of specific antibiotics on milk composition, et cetera. So the research questions that are being answered in this clinical project are commonly used antibiotics taken by lactating individuals associated with changes in the maternal or infant microbiome or metabolome, changes in milk macronutrient content, or in the human milk oligosaccharide profile. And if there are changes, are any of these associated with a specific antibiotic PK profile that's being assessed by one of the cores in our MPRINT center. And then a third objective is, can antibiotic exposure through breast milk be monitored non-invasively through skin swabs, so a little easier to capture. So the aims are to determine the pharmacokinetics of 4 commonly used antibiotics in breast milk samples from women who are treated with those antibiotics, to compare milk composition, oligosaccharide and microbiome profile of the mother and infant in the antibiotic treated mothers to those who are not, and then an exploratory aim to look at growth, neurodevelopment, and incidence of serious and non-serious infections in the first year of life in infants breastfed by individuals treated with antibiotics versus those who are not. The methods involve enrolling about 500 breastfeeding individuals in the standard HMB protocol in the first 3 months postpartum, and to collect baseline samples from that entire group. And then via weekly contact by text, identify individuals who do get prescribed one of the target antibiotics, and then to reconsent the first 40 that we identify as treated, being prescribed an antibiotic, to collect serial milk samples and other biospecimens, and that at the same time to reconsent 40 matched non-antibiotic treated individuals matched on infant age to the antibiotic treated group, and they would receive the same post-baseline collections as the treated group. And then finally, a smaller group of 20 non-breastfeeding individuals who are treated with antibiotics and obtain samples from them. So the schema is shown for this sampling type and the timeline, baseline, the start of antibiotics, mid-treatment, and the end of treatment. So group 1, who is breastfeeding and treated with antibiotics, will provide a milk sample, fecal and skin sample, and a sample captured from the environment like the bedding. And then the same samples would be collected on 3 additional occasions once an antibiotic is prescribed. And then the first comparison group is individuals breastfeeding but who have not been treated with antibiotics at any time postpartum. So the same baseline and 3 post-baseline assessments as the treated group. And then the last group, not breastfeeding but treated with an antibiotic, of course, same serial sample collection, but no milk involved in those particular sample collections. So we've just started this now, and are optimistic that we will be well on our way this year to recruiting the majority of the people in the baseline group. So I'll end here, and certainly happy to take any questions, as I know Lars is, and here are ways that you can contact us or contact the biorepository if you'd like more information.
All right, great. Thank you both for your presentations. We do have a couple of questions in the chat and the Q&A. First, I think this was going back to Lars' initial presentation. What percentage of prescription medicines that are used in these populations were prenatal vitamins?
I don't know, to be honest with you. I don't know what the percentages of prenatal vitamins that fall into those statistics. Tina, do you know more about that?
Yeah, it's very common, of course, that individuals will continue taking them, but if you look at the number of medications that an individual who's pregnant or lactating uses, it's typically in the 5 to 10 range. So the prenatal vitamins is maybe part of that, but it's certainly not accounting for all of the exposures that are taking place.
Yeah, my feeling is that number did not include prenatal vitamins. I think when you include that, it gets, at least for the pregnant side, it gets closer to 90%, and I think it was about 60% in the slides here. So, and then how long in the marijuana study, how long are you following up on the children for the outcomes?
They're being followed till 3 years of age, with neurodevelopmental questionnaire testing and face-to-face testing. So we think it'll actually be the first study that actually has that type of follow-up. There's only been 2 very small previous studies following to 1 year of age that have been published so far.
Great. And then there's another study in the Q&A, and then several in the chats, but in the Q&A, nice presentation. Are you measuring cholesterol composition, protein, lipids, and pH, as well as dynamic changes in these parameters during breastfeeding? such as high milk and fore milk differences and over time?
So answer is yes, but not always. So for some studies where we specifically go after early life or early milk and looking at the dynamics over a short period of time, we have done that. That's not part of the human milk biorepository necessarily, but in other studies, we've looked at colostrum, we looked at changes over a short period of time, even within the feed, hind milk, fore milk. We are not necessarily looking at proteins, lipids, and pH with a high focus, not yet. We're mostly looking at oligosaccharides. So I can tell you there that that's extremely constant over a short period of time, and certainly between fore milk, and hind milk. But others have done that. So that's nothing new in the field. Others have looked at proteins, lipids, and many other variables and components in colostrum over time. So that data certainly is out there.
I think a follow-up question I had on that was actually in the COVID vaccine study. Did you look at milk composition in those who received the vaccine? Yeah,
so we have started doing that. And we actually have a few people in the lab working on that as we speak, literally as we speak. And there we have started looking at oligosaccharides. No data to report there as of yet. But we're also looking at macromolecules, proteins, lipids, calories in general. I know there's data on calcium, lactose. So that's something that's in the making currently.
And then going over to the chat questions, do you know if any of the pharmaceutical companies are working on human studies of the oligosaccharides that you mentioned for RA and CBD, the three salicylate complexes?
So some of the stuff I cannot reveal, as you can imagine. Yes, there is a few companies working on that right now in the adult space, but certainly when it comes to the infant formula space, I don't think there's any company out there that's not working on oligosaccharides right now. And some other comment was here in the chat that Abbott launched a formula with 2FL. Most other formula companies also have 2FL and a couple of other oligosaccharides now in some of their products. 2FL is maybe a little bit of an interesting story because not all women make 2FL. If they make it, they make a lot of it. It's the dominant oligosaccharide. But about 20-25% of the population does not make 2FL. So of course we don't distinguish there when we make infant formula. There we put it into all infant formula, right? Very low concentrations at this point. So I would argue, we're actually adding something into the formula that is not in some of the human milk, and we don't know exactly what consequences that has. So 2FL is a bit of an interesting one.
Can I ask a question, Lars? So would it make sense to look at 2FL in maternal blood prior to delivery and then determine whether or not it needs to be supplemented?
Yes, we could do that, and we could actually use that sensor that we just published on 2FL. So that's very easily find out. You can see it if mom has a genetic testing already. You could see whether Q2 is active or not, and whether mom is a secret or not. But my real question is do we need to do that? Because that makes the assumption that moms that don't make this oligosaccharide, there's something wrong, there's something insufficient. And I don't think that's the message that we should convey. I don't think that the so-called non-secretors, there's anything wrong with them. There's a reason why we have those non-secretors. And in certain parts of the world, 40% of moms are non-secretors that don't make this oligosaccharide. There's probably a reason for it.
Right.
And then there's another question in the chat about the complexity that we see with any natural product and not necessarily knowing, is it a single compound in the breast milk, such as 2FL, that's causing or that's resulting in the effect, or is it a combination of multiple components of it? So I don't know if you have any thoughts on that as well.
Yeah, that's of course a huge research question right now, right? Is it the sum of individual components that's doing certain things? And if we had all those components, we will not have all those components, but if we had some of them or more of them, does it make infant formula so much better that we don't have to breastfeed anymore? And that's, I think, the quintessence of the question there. And it's not that simple, of course. There is no human milk. Human milk composition varies greatly between different women. So which composition do we take? Do we just take the average, or is there a reason why we have that variation? Also, it changes over the course of lactation. So do we constantly have to now adapt our product, so to speak, to follow that trend of how human milk changes? And then let's not forget, the benefits are not just for the infant. The the benefits of breastfeeding are also for the breastfeeding mother. And by now disconnecting mom from infant and introducing an infant formula product does not take care of mom at this point, right? So all those benefits for mom will not be there by feeding something to the infant. So it's a very complex question. Yes, but of course, we're trying to make infant formula better because we know there is infants that receive infant formula. But at the same time, we are very well aware that we'll not be able to mimic everything that breastfeeding and human milk can do.
Great. And then a couple of final questions. First, Dr. Chambers, could you put the links for the last slide of your presentation in the chat so others can find it easily? And then another question relating to study design. What are some of the challenges of using human milk for pharmacokinetic studies?
I think Jeremiah Momper is the person who's leading that for our group, so he would probably be the better one to answer it. But I think probably some of the challenges are trying to identify what is the best schema for sample collection without overburdening the participant. So obviously, and allowing them to continue to feed their baby if they're going to. So, and it's certainly with this clinical project here, they're designing a sample collection schema that varies by antibiotic because the metabolism of them are different and the length of time they're prescribed is different and so on. But I think at least from our perspective, that would be one of the challenges is how frequently and how over what period of time do we need to collect these samples and how much of a sample do you need to be able to address these questions?
And I think maybe to add to that, it's also a question of being able to measure the volume that actually goes into the infant during every feed and then over the course of a day. How do you actually measure exposure if you want? How do you measure just concentration? Then now going back to total amount that came out of human milk when it comes to PKs. And also human milk is not plasma, it's not urine, it's a very different matrix. So analyzing something in human milk is not as trivial as taking the same assay that you use for plasma and now using milk samples for it. It needs to be validated accordingly. And I think that's where a lot of studies fall short because they just treat human milk like any other matrix without thinking that there's a bunch of fat in there. And that comes in a very different presentation than it does in plasma and other fluids. So I think that's certainly a caveat there too, to know how you're measuring something and then how do you deal with this volume issue.
Right, I'll echo that last statement you made, Lars, about it's not the same matrix, and even colostrum versus more mature milk is very different matrices and not necessarily the same when you're measuring it. So from an analytical standpoint. I don't see any other questions in our chat. So I would like to take this opportunity to thank Christina and Lars for joining us today and invite you to attend our next webinar in 14th and at the same time, and hope to see you there. Thank you.
Thanks for having us. Thank you.
Everyone.